Thank you very much. It's really a very exciting opportunity for me to be here. I'm delighted that the committee decided to choose Raghu, and I'm lost for words. Anyhow, I want to tell you a little bit today of a story that certainly started with the work of Struck and Varadhan on the martingale problem. I'm going to spend some time trying to explain to you, in language I can use later in the talk, just what that achievement was, or some small part of that achievement, and particularly to explain to you, in case you're not probabilists, how some of these results, although they're quite meaningful for probabilists on their own right, have implications for the way one thinks about PDEs. And then I want to leap, like the other speakers, into the present day and try and look at how some of these same ideas are important to some questions that we're looking at the moment. In fact, the final results I'm going to talk about there's going to be some solid theorems there, but because of those theorems, we're able to ask some quite new and fresh questions, and I'd be delighted if somebody in the audience were able to solve these problems over the next few years. So I want to start on the basis that you don't necessarily know too much about stochastic processes, and so I remind you a little bit that Brownian motion is really a measure, a way of choosing random paths, and that you can do things with it. Now, one thing you can do is you can look at the first time your path hits some set, and for example, if you draw those paths with the Brownian measure, you throw the dice and the Brownian path comes out, you can look at the probabilities, starting at your point x, that you hit this set. Now, in 2 dimensions, it turns out you'll always hit the set if the set has any substance to it. But in 3 dimensions or higher, which is why Ofer was talking about 3 dimensions being different earlier, it's a different story. So pretend this picture is in 3 dimensions. Then you get a function. You get a function depending on where you start that is clearly 1 inside A, if A looks like the A I've drawn in the picture. If A was fractal, it might be a different story. And which is defined outside, and at least in R3 will go off to 0 at infinity. In fact, it's quite well understood that this is the equilibrium potential of classical electrostatics. And we'll come a little bit more to why it solves the PDE problem in a minute. But before I do that, I want to point out something, that actually doing Markov processes rigorously, even doing this very simple problem rigorously, is a slight challenge. And the reason it's a slight challenge is because of the fact that it requires non-trivial measure theory. It's one of these things that once you realize the measure theory is there, you don't need to think about it anymore. But I just point it out because, you see, if I look at the set of paths that hit A, well, is that a measurable set, even if A is measurable? But if A is measurable, it can be ghastly, because measurable, you can modify things by null sets. But what if A is even Borel or open or compact? Actually, the point is that the function is a function from time cross paths into the space. That's the continuous function. So if I pull back an open set, yes, it'll be open. If I pull back a compact set, it can be pretty grim. But that's not really the point. It'll at least be Borel. The trouble is that if I look at the set of paths that hit that set, in fact, it's a projection. And a projection of a measurable set is ghastly. I mean, but not so ghastly you can't measure it. But certainly ghastly enough that if you project a Borel set, it doesn't have to be Borel. So actually, even to make sense of this little problem, even when that set A was a Borel set, would cause you some serious Bourbaki-style measure theory. Fortunately, as I say, once you've done this, you can forget it, because it says that as long as you never complete anything, anything you ever want will be in the completion. But it still requires it to make things rigorous. And one of the things I've found attractive about stochastic analysis from the beginning is this interaction between the applications and the rigor. Because probabilists deal with all these rich infinite dimensional examples, but I think they genuinely stay true to the idea that you really prove things. Now let me try and explain a little bit why that hitting probability is connected to PDE. You see, most of us have this understanding, even an intuitive understanding, of what a Markov process is. A Markov process is a process, it's a generalization of an ODE. It's a process that when you stop it at some time and then start it again, then where you've stopped it and the state when you stopped it is all you need to know to predict as much as you can about the uncertain future. In particular, you don't need to know what's happened in the past. Now, apply that to our little problem of the hitting problem. So I want to draw a little ball around X and look at the probability that I hit my set A, which is off the picture now. And I think you'll be convinced that the probability that I hit A averaged over the locations at which, careful you get feedback, averaged over the locations at which I leave that sphere should equal the probability that I hit A starting at X. Because there's no way I can hit that set A until I've left S, so I may as well condition on what happens then. And because of the spherical symmetry of Brownian motion, it's obvious you get a mean value property that the average of this function over the sphere is the same as the value at the point. So it's obvious it has a mean value theory property. It's pretty obvious it's continuous on the complement, and so it's harmonic, which is the Laplace operator. In fact, probabilists would probably prefer to say this somewhat differently. What they would probably prefer to say is it's more or less obvious by the same sort of arguments that if I look at the value at the final time and take its conditional expectation onto the time when I first leave the sphere, I get the value back when I first leave the sphere. This is actually saying that in some sense the value of this function is a fair game wherever we are. On average, it will be the same in the future as it is at the current time. The probability of hitting at some time when I'm sitting at some point in the future, the expected probability is going to be the value of my function at that time. This is what we call a martingale. A martingale is really a PDE, a solution to a PDE. It's a harmonic function, if you like, but it's a harmonic function on path space. The idea is that you lift your problem up to a problem on path space, and because path space is fairly generic and not too sensitive to the particular manifold or geometry, there are a lot of things you can do on path space quite accurately that are a bit difficult to do in the less generic, less universal settings. So martingales are really harmonic functions on path space, and the idea is that when we compose this function with our path, we get a function on path space, and it's a martingale. So the attraction of that approach can be seen most clearly once you put Ito side by side with it. You see, Ito does not just work with Brownian motion. Ito took Brownian motion, this spherically symmetric diffusing process, and showed us how, by looking at stochastic differential equations, we were able to build lots of other processes. So if we have a collection of vector fields, then we can look at the control problem where Brownian motion is the input, and we move in some random combination of the vector fields plus some deterministic behavior of an ordinary differential equation, and the output is another Markov process. It's intuitively clear that the only thing we need to know to work out where we'll be next is where we are now and the Brownian path between now and next. So it produces another Markov process. It will not have, in general, this mean value property in the spherical sense, but we can still compute hitting probabilities, and we can still use that sort of martingale strong Markov type argument to see that if we compose that hitting probability with our process, then until we hit the boundary, we actually get a harmonic function, a martingale. So you see, martingales become a way of testing whether something is the solution to a second-order differential equation. And now, because of our Ito power, we can do a vast number of non-constant coefficient PDEs, as well as the constant coefficient case that comes from a detailed study of Brownian motion. In fact, of course, we can do better than that, and many of you, I apologize for have seen this 1,000 million times, because this is a sort of core part of stochastic analysis. We can start with a function on the boundary of our domain, and instead of taking the hitting probability, which is just the expectation of the function 1, we could take the expected value of f of xt. It's the same sort of measurability problems, but these are neither here nor there, once you know about Bourbaki. And you can define a function. This function will, when composed with the process, give you a martingale, so it should be harmonic, and indeed, using Ito formula, you can see it also solves the PDE. And it gives you a good way to go between the probabilistic processes and solutions to PDEs. But I want to emphasize for you that in some respects it's a little bit more robust. So let's look at an SDE, a rather trivial SDE, simply the one that rotates you. So wherever you are, you move perpendicular to your direction to the origin. So you do a sort of semicircular motion. Now the reason this PDE is interesting for this discussion here is you see it doesn't have any mixing properties. It doesn't spread out into the whole of space, it's quite singular. But it's fine from the point of view of an SDE, it's fine from the point of view of a Markov process. So if we repeat the problem and choose some function on some set, and here I'm thinking of a Cantor set, maybe positive measure, maybe not, and probably not for a minute actually, we can still look at the probability of hitting this set, and it will actually have constant values on sort of annuli like this, and it'll be 1 sometimes and 0 other times. If we put a function on the boundary, it would be more interesting on the annuli, but 0 everywhere else. It should, in some sense, be a solution to a PDE. It is, in the sense that if you compose it with Brownian motion, well, with the Markov process, you get a martingale. So it lifts to a PDE on path space, to a solution of a PDE on path space. But down on Rn, it's a problematic function, really, because if we write down the PDE, and I've written it down at the bottom here, well, we can. It's the square of this vector field, and this vector field is going on in a circle. But of course, if we write it out properly, every one of those coefficients, every one of those derivatives is pointing you off the circle. So you see your function is 0, 1, 0, 1, 0, 1, and it's not differentiable. It's not even meaningful in the sense of distributions, because if C has measure 0, this function is 0 almost everywhere. So, I mean, the test measure of Lebesgue measure has no relevance here. You'd have to go onto the surfaces in order to make sense of everything, and then you could. But I wanted to capture the point that somehow the probability has no difficulty in such environments, whereas the PDE, intrinsically, because of the way we define it, tends to, because although the vector field makes sense, it flows along the circle, we tend to write it in terms of objects that no longer make sense. And I wanted to give you an example, actually, of something more deep, which I can't really talk about too much. Hopefully this will work. But this is a little program of a colleague of mine, Martin Barlow, and what it shows, I hope, is heat diffusing. But the heat now is actually diffusing on something which is very close to the critical percolation cluster in 2 dimensions. So you see it's a perfectly deterministic flow. It should in some sense be a solution to a PDE. And certainly we can associate a Markov process with it and so on. But the domain that it lives on is actually the critical cluster close enough of a percolation model, which is very fractal-like, which has no natural charts at all. So you see, there are lots of really quite interesting examples where the basic chart model that we're used to isn't actually terribly efficient. This isn't to say that when it is efficient, it isn't a very good idea. But here you see, by the way, you can think of this as pollution spreading out through a soil structure or something, and the large deviations are actually the bits at the edge where the pollution actually reaches to in its extremities, the small tail behavior. There's still large deviations here. Right. So that's to set the scene. Probability is quite a good way of testing whether things are solutions to PDEs because it's like the integral curves. It's actually staying in the domain where the PDE, the diffusion actually happens. Unlike the PDE, which is sort of paying too much attention to being an Rn. So now I want to come back to what was, I think, a classical problem, and one which Struck and Varadhan most definitely solved. And that was to understand equations like this, which turn up quite naturally in various control problems and so on, which is a second-order PDE of the normal sort of kind, nothing fractal, but with continuous coefficients in non-divergence form. And there is a sort of dichotomy between divergence form PDEs and non-divergence form PDEs, which cannot be seen until the coefficients get a little bit rough. Until then, of course, you can just switch them around and put everything into the B. But this is very much at the limits of these issues. And one would like uniform estimates. In fact, one would really like estimates which work whenever Aij were bounded, because then you could handle nonlinear situations quite easily. But anyway, we'll come back to what happens when it's just bounded in a little while. But I want to take the theorem that they proved, and the theorem really looked at the case where the AIJs were bounded and continuous, and actually uniformly elliptic, which I've expressed by saying that the inverse is also bounded, and where the drift, which doesn't really come into the story very much except to irritate, is bounded. It's a very reasonable question to ask, does this describe uniquely an evolution, a diffusion of heat, of pollution? Or, in fact, should there be some extra ingredients you have to put into your model before you have accurately described what happens? That's what uniqueness means. It's not something artificial. It's have you written down enough data to correctly model what you're interested in? And this was a serious open question, understandably. If the AIJs are wholer or something, you can do it, but the continuous case was absolutely the edge. And you can state it in probabilistic language, and we'll come back to that, but you can obviously state it in analytic language, and the way I think people would have stated it then, and probably even the way that people would state it now, is you have this natural map L defined on smooth functions that go to 0 to infinity, and it takes its values, at least if the B is continuous as well, and goes to 0 to infinity in the C0. And then you want to know whether you can close it, and whether you can close it in a unique way. Well, the answer actually is no, if it's just continuous. You definitely have there are definitely examples where there are different ways of closing it. So that already suggests there's a problem. But you want to know whether there's a unique way to do it so that the associated semigroup is positive. Because when things diffuse out, they don't turn negative. So the goal is to know whether or not you can find a unique closed extension which defines a positive semigroup. That's the analyst way of saying it. And the probabilist way of saying it is there a Markov process associated with it? And is that Markov process unique? But you can't say that quite yet, because the associated is too loose a piece of language. You see, at that point in time, the way that people tended to think about Markov processes is, first of all, they created the semigroup. So intrinsically, what people would tend to do is they would have said, we've got this operator, we've closed it, we've constructed a semigroup, we use the semigroup to construct resolvents and Markov processes, and that's the sort of way round the circle we would go. As I understand it, one of the ways that things were really changed by the Struck and Varadhan papers was they said, well, we have a semigroup. I mean, we have a process, and that's Krylov and people had proved important theorems in the same sort of area, and as a result, we know that there's at least one process associated with this object. The question is there more than one Markov process associated with this object? I've still not told you what associative means. Well, at least if you have a smooth function, that PDE tells you what L of it is. I mean, we know how to apply our operator to smooth functions. And now, because of what I've been trying to tell you before, we know how to express the fact that we know how to compute the second derivative of u, the operator acting on u, in terms of the PDE. So in terms of the probability theory. You see, we can just take our process and compose it like I did before. For the harmonic case, you get exactly that it's a martingale. But in general, you can say, well, it's a martingale plus a correction. And the correction is just h, where h is what you get by applying the infinitesimal generator to this smooth or C-infinity function. So for C-infinity functions, we knew, or they knew, that whenever they had a process associated with this operator, it should happen that when we compose it with a smooth function, we get this relationship, that you get a martingale plus something which we understand. Bounded variation, no stochastic calculus, no nothing. In fact, it was far more ingenious and far cleverer not to consider all smooth functions, but just to consider the ones associated with the heat equation, and in particular, the exponential functions that would generate exactly a martingale. So what they did is they said, we've got this process. We know, because the smooth functions are in the domain, that these exponential functions should generate martingales. Can there be more than one process with that property? And using Calderon-Zygmunt theory and quite non-trivial analysis, so at that point, this wasn't just a game of probability theory, this was a game of taking the best of both and putting them together, they were able to prove there was only one, the uniqueness of the martingale problem. And in particular, they were able, therefore, to prove that the elliptic operators with continuous coefficients that are strictly elliptic and so on have the unique semigroup associated with them. Okay, so that was then. And now I'd like to, well, actually I've forgotten. I just wanted to do one thing first and tell you how the world has changed since in that problem. I mentioned at the beginning that everyone would have much preferred to have bounded measurable AIJs. And I think everybody thought that it was really just the difficulty of the proof that Struck and Varadhan had produced that was stopping one getting the bounded measurable case to be unique. Well, actually, that's not true, because in a very nice paper in 1999, I think it was, Nadir-Shvili gave a counterexample to show that in the elliptic case, you did not have uniqueness. There is more than one. This differential operator does not tell you the story on its own. But now I'd like to go on. I'd like to have some assessment of how I'm doing time-wise. Fine. What I'd like to do now is, in two parts, I would like to explain how this pathwise process, this pathwise understanding of solutions to PDEs can be powerful. And in the first part of this talk, the rest of the talk, what I'd like to do is explain how you can use it to get effective numerical methods. Now, most of you have heard, I think, of Monte Carlo, and what is surprising, it's still used in a large way for various technical reasons that I'll go into later. But I'm going to try and describe ways that look potentially a lot more efficient than that, and in doing so reveal some interesting new mathematics. And then afterwards, I'm going to ask you really whether or not this bonding between probability and second-order differential equations is quite as rigid as it looks. And I'm going to explain to you how quite a lot of what I'm going to say can be lifted up to a relationship between certain measures on paths and new numerical methods on the one hand, and higher-order PDEs of the sort of Lax and Milgram indeed studied when they looked at the semigroups. So the second part of this talk is what's left is going to be higher order PDEs, and the first part is sort of setting the scene, because it's a set of methods I'm going to introduce there that in some sense can be carried forward. Well, I've already explained to you that a key step, a key reason for the importance of Brownian motion is that it's a very specific object, you can study it very intensively, and yet, because of the Ito-stochastic equations, you can use it to model many other diffusions. So you split a problem of understanding another diffusion into two parts, understanding how to solve an SDE on the one hand, and Brownian motion on the other. And you can solve the PDEs associated with the stochastic differential equation by taking the expectations of the value at time t. So the semigroup that would give you the value at time t of your PDE given the initial data f at time 0 is simply the expectation of this solution to this SDE, started at x. And because we know how to do these things numerically, even you should actually be able to build sort of naive models that would, a bit like my picture, solve these differential equations if you knew the first few things about simulating stochastic differential equation solutions that you find in the basic books. It's not very deep or difficult. But what I want to do is I want to challenge you to the possibility that there might be much better things that you could do. And the story I want to tell you is in part, and I think initially, developed by Kusuoka and Inomiya, but we added certain significant things, so it was then carried out by Victoire and myself, a student of mine. And the idea is that rather than randomly choosing paths in Wiener space, you say, if I'm trying to solve a PDE of this kind, then really I'm trying to do an integration. If I were doing an integration on the line, one thing I could do is randomly sample, but another thing I could do, which is much, much cleverer, is say, well, actually, the function I'm trying to integrate is moderately smooth, and I would use cubature. I would use quadrature. I would put points and weights carefully down on the line, the right number of them and the right weights on them, very, very carefully chosen, so that I integrate polynomials exactly the same for my discrete measure as I do for the Gaussian measure, say. And this is actually a very effective numerical method. You have to work to find the points, but it's not a bad way at all if your functions are smooth. Well, the idea is to try and do the same on path space. Path space sounds a horrible infinite dimensional space, but still you can actually do something really quite useful. So the idea is that you want to find a finite collection of paths and weights on those paths, so that if instead of solving my differential equation for y along every Brownian path and taking the expectation, we just solve it for these specific paths, and we evaluate our function at these specific places, and we take the expectation with respect to these specific weights. And then the idea is to choose these paths in such a way that you have a high-order approximation providing your f is smooth. And this is actually a wonderfully good idea because the heat kernel smooths. So even if it's wrong and you start with Lipschitz initial data, if you iterate this process, after the first time step at least, you have relatively smooth functions. So high-order methods work. And so this is actually a story that has been put into practice a bit. But to tell you how to do it, I have to introduce a whole load more structure. So now I'm going to try and tell you about some more structure, and then we're going to come back to telling you how you can do it with the structure, and then to the high-order methods. Elementary probability, well, all analysis needs finite dimensional objects to look at. You can't go and look at paths. You have to find some way to describe them and look at them. And in elementary stochastic processes, what people tend to do is they tend to look at cylindrical functions. That is, they tend to look at functions of where you are at a finite collection of times. This is not a bad idea at all. And one of the reasons it's a good idea is it forms an algebra. The class of these functions is an algebra, and so hidden inside it is the Stone-Weierstrass theorem. So if you define some operator on this space, then actually it's always going to be a relatively good space. The main problem is it never gives you any information about direction things are going. So line integrals, things like that, stochastic integrals are not so well defined. It tells you where things are, not the direction they're going. But there is another class of functions which was introduced by the geometer K.T. Chen a long time ago now, and has been looked at by other people as well. Magnus looked at them, but a lot of people have looked at them. At least if you have a path of finite length, then you can look at what I would call coordinate iterated integrals. So the idea is that maybe take a multi-index and let I be I1 up to Ik, and then you take the projection of your path onto these different coordinates, so it's real valued. It's finite length, so it has a derivative almost surely, or at least we can reparameterize it so it does. And then form this iterated integral over a wedge, over a simplex. So it's very much order dependent. It's the products of the increments, it's products of k increments that are disjoint and increasing in time, and the sum over all such increments. So this is what I would call a coordinate iterated integral. Now these are functions on path space too. They're slightly different though, because unlike the other ones we said where everything was in time, these ones are completely parameterization independent. If I reparameterize my path omega, then actually I don't get a different answer for this phi. So these ones measure paths without parameterization. And for various reasons, mathematical reasons, it makes much more sense to put them together. So rather than taking the coordinates once at a time, it's better actually to take the full tensor product. And so look at the dual object, if you like. This is functions on path space. This is one object associated with my path. So I take my path and I represent it as the 1 plus the integral of w, so that's a vector, that's the increment. And then these higher order terms, which are successively higher and higher tensors. So the whole lot is in the tensor algebra. And then you see these coordinate differential integrals are just simply projections of it using elements in the Thule space. Now, I want you to get some feeling for these objects because they're quite important. The first ones, as I said, the first order terms are simply the increments of the path, or their coordinates. The first time you start to see something a little complicated is in the second term, where you have two indices. And the reason it's complicated is, well, if you look at certain components, for example, the symmetric ones, there's functions of the first order coordinates. So you're not gaining new information. But if you look at the antisymmetric ones, but this is far too simplistic a presentation, then actually you get something new. Because you get the area trapped between the path and a chord. And if you wonder what that means in d dimensions, it's an antisymmetric two-tensor, so any projection onto 2 dimensions will produce you a curve in R2, and then you can compute its area. It turns out that these two functions, the coordinate iterated integrals on the one hand, and this signature on the other, are very fundamental objects when you're looking at paths. So the coordinate iterated integrals, these are these real valued functions on path space, form an algebra, just like the cylinder functions did. And in fact, if you take the product of two of these objects, then what you do is you shuffle all the indices, and you take all possible shuffles and add them up. It's called the shuffle product. And it's an abelian product on the cotensor algebra. But equally important is the map from the path into the signature, which is a map from paths into the tensor algebra. And it's really important because it's actually a homomorphism. If I concatenate two pieces of path in my vector space, that's a product. And if I look at their images in the tensor algebra, then in fact, you get the tensor product of the two signatures of the components being the signature of the concatenation. And also you get the fact that if you run the path backwards, you get the inverse. So you see that it's the range, the target, is closed under multiplication and has inverses. It's a group. It turns out these objects are surprisingly powerful for capturing information about paths, even at a quantitative level. It sounds very abstract, but it's not terribly. And I have this little program, which I hope will allow you to get some feeling for it. So, to get rid of all the algebraic dependencies, you take the logarithms in the tensor algebra, and you end up with Lie elements. That you don't need necessarily to follow that very much. But what I'm going to do here is I'm going to draw paths, I hope. The little program I drew. Right? And at the top here, you see the first few terms in the log signature. So basically, if I move in a straight line, then I get some contribution to the x-coordinate, a small contribution to the y-coordinate, no area significantly, and so on. If, on the other hand, I do a loop, then, of course, I get no increment, but I get a substantial area. If I went round the other way, it would change sign. The reason I get this program is partly to convince you these are things you can really calculate, and they give you real information, but also to help one understand the third component. So if I do something like this, then this has an area, but the area comes at the beginning. And if you look at the signs of these last two terms, that's what I care about, they're both negative. If, on the other hand, I did it the other way around, one's positive and one's negative. You see, just as the area captures something, these terms capture more sophisticated order information about the events in the path. So, taken as a sequence as a whole, they're very powerful description of your path, but they completely ignore parameterization. I hope we can get the next slide. I really hope we can go. Yeah. Right. In fact, they capture the path completely, up to reparameterization. And I'd like to tell you about that very briefly in a minute. But I want to explain first how you can use them. I want to explain to you first how you can actually use these information to produce better and better approximations to your differential equation. So if I have a path gamma, this path of finite length, and I go away and compute its signature, and I go away and take its logarithm, so the first is the increment, the second is the area, the third of those terms I just showed you, then how can I use those to produce better and better approximations to my solution to my differential equation y? Well, the idea is actually quite a simple one. You take your differential equation, which is time varying. The whole point is that gamma is continually changing the direction in which you flow, and you try and replace it over your period of time by a time homogeneous differential equation. So you have this complicated dynamical system that's always changing its directions, but you want to replace it by a much more trivial dynamical system, one that doesn't change its direction with time, and you want to integrate that. There's lots of good reasons for doing that, because you can then pull out your standard favorite symplectic ODE solver in order to do things, and but also because we know how to do it. So here is how you would do it, and I want you to see how the Lie terms fit in. So the first attempt would be to ignore this term here. You see, we just take, if we take the increment and contract it with the vector fields, we get a vector field. So we can construct an ODE, which is simply the average of our vector fields, where the weights are given by the increments and not infinitesimally. But if we include the area, then the area is an antisymmetric two-tensor, and we can contract it with the Lie brackets of the vector field. So this is another vector field. The third term, the fourth term, the fifth term, and so on, every one of them is a Lie element. Every one of them has a natural contraction with your vector fields to produce a more and more sophisticated vector field, producing a more and more high order, not necessarily better if you're outside the asymptotic region, but a higher order approximation to your flow. In practice, if you are in the little region, it can be a very good way to do things. But one thing you should notice in this picture is a separation. I mentioned before the idea of separation, but we have it again. You see, we have a very nice separation between properties of our driving noise, our control, and our differential equation. The information we needed about our control is completely independent of the differential equation, which is very good, because if you're constructing a flow, then moving to different locations means you're basically solving different differential equations. It gives a canonical way to think about your noise, your path, separately from your differential equation. Anyway, that's actually how you use this extra data, and I'm going to use it to get a high-order numerical method in a minute with this Monte Carlo. But I'd first just like to explain to you the pure mathematical result, which is that this log signature really is an invariant of your path. You see, if I have a path gamma and it's controlling my system, there's one sort of path that has no effect at all. And that's really a tree. If I roll a football without slipping along a tree like this, then it should be relatively obvious to you that by the time I get back to the beginning, I might never have bothered. If I solve a differential equation driven by a path that is tree-like, it has no effect globally over the whole time period. Of course, it does things in the middle, but the global effect is trivial. And you can define this tree-like notion in an analytic way, not just by drawing pictures. And you can define it in a way that allows you infinitesimal and countably many little perturbations. And once you do, you get a nice closed set of tree-like paths. Well, the basic theorem that says these statistics are good statistics of your path is a theorem that says, and Chen proved it for piecewise smooth paths with certain extra conditions on them, but we proved it for paths of finite length, that two paths have the same signature if and only if the first one given by the second one run backwards is tree-like. And given the homomorphism, that's the same thing of saying a path has a trivial signature if and only if it is tree-like like this. And this is mixing the algebra with the analysis. It's sort of a non-commutative analog of Fourier series. Fourier series say if two functions have the same Fourier series, not if they're equal, but if they're equal up to a null set. The right class of null sets for this control problem are these tree-like paths. And this is an algebraic transformation that captures all that's important over the effect over the long time interval of these paths in term for the control problem. So now I want to try and explain to you how you can use these ideas to do numerics, to produce high-order numerical methods based on the sort of concept of Monte Carlo, which has its attractions because it stays in the legitimate region. Unlike grid methods, it doesn't bleed off the surface, and you can use your symplectic methods as well if it's Hamiltonian and so on to stay inside. But it doesn't have the wastefulness of Monte Carlo because it tries many things too often. So the idea is that each path has a signature. Each Brownian path has a signature. This is a nonlinear lifting of your path into the tensor algebra, but the algebra is a vector space. And we can take the expectation of this signature, and we can truncate it at each level. And the remarkable fact is it has a very nice form for Brownian motion. And I've written it here. We're going to come back to that later, so you don't have to worry about it too much, because that's how the higher order operators are going to work too. The remarkable fact is it has a nice form. So this is an infinite tensor. It's E tensor E, where these are a basis, and exponentiated. So it has tensors of all order in it. And so now we know what our path should do. You see, we're not looking for a Brownian path. This is the expected signature of a Brownian path. We want a finite collection of paths that well represent the events that happen in a Brownian motion and capture them in the right order. So what we look for is a finite collection of paths, a minimal collection of paths, which, when we compute their signatures and we put the right weights in front of them, have the same expectation. We obviously can't get that for all terms, but the same expectation on the first n terms. So this way of looking at things, this non-commutative algebraic way of looking at things, gives us a way of forcing on our collection of scenarios the fact they well represent what can happen. And this actually can be done, and one of the crucial features about this problem is that the number of paths you need, well, it grows nastily if you let n increase, very nastily, but if you let the dimension of the space increase, it doesn't grow so nastily. In fact, it grows polynomially in the dimension of the space. And many of the applications are in finance at the moment, and finance is generating more and more moderate dimensional problems. In fact, one of the interesting challenges coming out of mathematical finance is the fact that the dimension of the problems that we're trying to solve is not 3, it's 10 or 5 or 15, often impossible, but not always. And for example, in a trial working out of this, not perfect, it has problems. Victoire and Inomia got 4 significant figure accuracy on a 3-dimensional interest rate model, which only had 2 dimensions of noise. So it lived on a surface which is quite natural in these finance models. And they achieved, I think, either a 10 to the 5 or 10 to the 6 speed up over the standard industry models. So they moved it from 10 to the 5 seconds to 10 to the minus 1, I think, which is sort of really quite attractive, but it was definitely still at the prototype levels. So now, in my last 10 minutes, I'd like to change the game again. You see, I've been explaining to you how these functionals on path space capture order information, allow one to do efficient numerics. But now I want to look at higher order problems. And by higher order, I mean 4th order PDEs and so on. But always at the moment scalar valued. I mean, this isn't to say one couldn't think about systems, vector value systems, but I'm not talking about them here. And I want to take the same philosophy that happened in the probability case. So I want to start by looking at the constant coefficient case, which was Brownian motion in that case, the translation invariant problem. And then I want to use stochastic differential equations as a way of moving our understanding from the constant coefficient PDE to the non-constant coefficient PDE, and to develop numerical methods and other ideas that might work in the non-constant coefficient case out of our understanding of the constant coefficient case and our understanding of solving differential equations driven by paths. So I want to take the sort of PDE that behaves well, in the sense that you can use harmonic analysis to define a kernel, and that the kernel is a bounded kernel, and so on. And basically the sort of information I need. Originally we needed With a bit of help from Bruce Driver recently, we've managed to get it down really just as insisting that the polynomial grows at infinity. It doesn't have to be real, but its real part, the appropriate part, should grow at infinity faster than any logarithm, so that e to the minus it is in Schwartz class. And then, of course, we can construct a semigroup. I point out, because we had some very dangerous bends at the beginning, that polynomials in many dimensions can be very strange objects, at least for ignorant peasants like myself. I thought that probably like in R, any polynomial that was strictly positive and went to infinity would have to grow at least quadratically fast. But here is an example of a positive polynomial which grows as slow as you like, at least along some sets of points. Anyway, we have one of these polynomials, and we associate it with a semigroup. And we do what we did with Brownian motion. We use it to construct a measure on cylinder sets. It's a finite measure. And, well, what goes wrong? I mean, the experts in the audience will know what goes wrong already, I think. But this idea of looking at this measure on finite dimensional sets, cylinder sets, is an old one. It goes right back to Krylov. He looked at it in his thesis and did some very elegant calculations in the case where you take the quadratic, the 2kth power of d by dx. But it goes wrong essentially because the kernel is not positive. It still looks very much like our Gaussian bell-shaped curve, but it wiggles a bit at the edges. And in particular, it goes negative. It also fairly obvious it integrates to 1. So that means that, in fact, if we put mod signs around it, it integrates to something bigger than 1. A little bit of exercise will show that, at least in the homogeneous case, when you scale time, it doesn't actually affect this integral at all of the total mass. So, in fact, when we took the product of those measures, we had a total mass, once you put mod signs around everything, that was c to the r, where r was the number of time points in our partition. We had a mass that explodes exponentially with the number of time steps in our partition. Now, that sounds grim when you take the limit. But who said anything about taking the limit yet? And if we don't yet take the limit, we could view this as a measure on paths. Piecewise linear paths. I mean, we've fixed where it is at certain times, and rather than think of it as a measure on all paths and so on, just let it be supported by the path that is piecewise linear, except at those times. So now we have a sequence of measures, and each measure is supported on piecewise smooth paths. The total mass of the measures is exploding as we put more time steps in, but let's not think about that for a moment. Because each of those piecewise smooth paths, we can analyze its signature. We can compute those iterated integrals. These are functions on path space that don't pay any attention to how we parameterize time. So we fix 0 time and fix time 1, and we put this piecewise linear path in between, but the functionals we look at are these iterated integrals. And the remarkable fact, I think it's remarkable, is this is actually a theorem, under the hypothesis I've stated, is that if we now let the time steps go to 0 in any way, we let the partition go to 0, so that the max of the time steps is getting smaller and smaller, yes, the total mass of these measures explodes, but when we integrate it against these test functions, the limit of the expectations exists. So in some sense, in the sense of distributions, but we have not yet made that precise, there really is an object in the limit. Perhaps, although we have not got a proof, there is really a measure on the unparameterized paths that is similar to the Brownian Wiener measure, but associated with each of these objects. It's a signed measure. But the one thing we do know, and this is perhaps a little bit surprising, and this is more or less, I think, where I'm going to finish, is that we can really compute these expectations. So it's just as we could compute the expectation of the Wiener case, it was e to the sum of the EI tensor EI, and we were able to build numerical methods out of it, it turns out that we can do exactly the same thing here. For every one of these constant coefficient differential equations, we can work out exactly what the expectation of this signature should be in the limit. So it's as if we've computed every moment of these measures. And all we need is the measure with those moments. But it's a signed measure, and I don't think it's a trivial problem, because we used the worked example of Levy area, and we used the moments the way they were expressed here, and went back to proving it was really the same as Levy's Levy area, and it was a highly non-trivial exercise in combinatorics that my postdoc Daniel Levin has just published with Mark Wilden in the Transactions AMS. So it doesn't look as if it's going to be a particularly easy story. But let me tell you two things, and that's the time to finish. I want to tell you, first of all, what is that expected signature, and I want to remind you how even if the measure doesn't exist in the limit, one should be able to use this to produce effective path-oriented numerical methods for solving these PDEs on the basis of it. So you don't have to know there is a limit to get these things out, although it's certainly extremely interesting to prove there was one. So first of all, what is this object? Well, what is the object that's the expected signature? Well, it's also e to the minus t times something. It's a semigroup because of the independent structure and because that works for sign measures too, the semigroup structure. But what is this W? Well, actually, it's quite interesting. If I start with my vector space V, this is the space where my paths live, where my constant coefficient PDE lives, I can construct a highly nonlinear map into the tensor algebra simply by taking the exponential of V. I take 1 plus V tensor V over 2 factorial plus V tensor V over 3 factorial. So the exponential map. If you think about that in coordinates, then actually it's writing down every single polynomial that you could write down in the coordinates. But because it's a function on V with values in a vector space, I can apply my differential operator to it. And remember, it's a constant coefficient differential operator. Constant coefficient differential operators work well with polynomials. They reduce the order. And some of them go to 0, some of them go to constants, and some of them stay polynomials. If we evaluate at 0, that L of G, then it kills all the high-order polynomials. L has already killed all the low-order polynomials, and the only things that are left are the polynomials that got differentiated by L into constant functions. And so W is actually exactly that. It's L, this constant coefficient PDE, applied to all these polynomials, and then you set the coefficients in the polynomial equal to 0, and you see which tensors you end up with. So, for example, if L is d by the x squared plus d by the y squared, then that will kill this one. It kills this one. It rubs out the x squared to leave E1 tensor E1. It rubs out the y squared to leave E2 tensor E2. And that's all you get, because anything else goes to 0. So you get this E1 tensor E1 plus E2 tensor E2. So that is actually the term. And that is actually the PDE that you'll end up solving. So if you now step forward to the numerics of PDEs, you can solve your PDE along one of these paths. You can choose paths, for example, whose signatures have this expectation. And you can solve the ODE along the vector fields. And you can take the expectation, and you would expect it to be a very good approximation to actually this non-constant coefficient PDE here, obtained by taking this polynomial in the vector fields given by W. So it seems that this pathwise representation of PDEs, which has certain disadvantages but certainly has robustness advantages, is something that should carry over to some higher order PDEs. I think that's all I wanted to say at this point, except I wanted to acknowledge that we are by no means the first people to work on these higher order PDEs and their links with probability theory. Working with Krylov as the beginning, a number of people have done this, particularly Hochberg. I don't think they've tried to mix it with the signature, and I think this is quite significant. That's all I really wanted to say at this point. Thank you very much.
Try to do Feynman integrals this way?
Sorry, if I can.
Can you try to do Feynman integrals this way?
I've been asked this several times, and the answer is I must try. I see no reason on earth why one should not be able to, but that's because I haven't thought about it. No doubt when one tries, one will find some reasons. I don't know. I don't see why offhand.
Variable coefficient.
Sorry?
About variable coefficient. Coefficients that depend on x.
Coefficients?
It is not constant coefficient.
Well, the whole philosophy here seems to be to understand the constant coefficient case first, and then the non-constant coefficient case. In fact, one of the questions I really want to work on is simulated by your support theorem, because it seems to me clear that the approach should lead to a uniqueness criterion, because you're basically going to take some sort of expectation of a solution to an SDE, and it's going to produce a solution to the PDE. But the natural object is the SDE, not the PDE. And I could believe, but I don't know, that you could find different families of vector fields producing the same PDE, just as you can in the classical case with the sums of squares. But what I don't see offhand is why the reachability manifolds of these different collections of vector fields should necessarily coincide. So you may actually find that the PDE does not represent what you mean by a solution, that the flow is more fundamental, and that you get different support theorems for different collections of vector fields. I don't know if that's true, though. I mean, I really don't know if that's true. What I've said, I think I know.
Any other questions? Okay, if not, then I think Terry wanted to say.
Yeah, I think I do. Well, first of all, like Ofer, I just want to say thanks on my own behalf. I'm fantastically honored to be here, and very pleased to be able to say thank you to you for concentrating and attending our talks. I'd also like very much to thank the Abel Foundation and their hard work in the prize process, and particularly in making such a wonderful choice. But even if they've made another one, I'd still like to thank them, I think, for their very hard and conscientious work. I think we're all very grateful for the support that has been in making this thing happen, in finding the money, and arguing with governments and persuading everybody that mathematics is important. And I'm sure that some of us have experienced wonderful hospitality from them, and we'd like to thank them for that too. I guess we should thank the university for this. But I'm sure we should thank Ida and Anne-Marie. Ida for making it work on a daily institutional, I don't know where she is, but she's here somewhere. Just making it happen. You know, like when lunch wasn't there today, I could see her stressing, and but it happened, didn't it? And so I'm sure we should thank Ida, and I'm sure we should thank Anne-Marie too, who's working very, very hard at trying to create publicity for this event and help the world at large understand the importance of mathematics and the importance of Raghu's contributions. And I'd like to thank Raghu himself for for what I said. Okay, so thank you very much to all of you.